Okay, so the topic of this lecture is circuit diagram and matrix multiplication. So right now we will discuss how matrix multiplication is playing its part and how it actually works with quantum operations and how it actually shows and represents the interference vector and behavior inside its multiplication law. So basically right now we have a line showing a quantum system and we have two quantum operations A and B. They can be anything, any gates, and this is not something to worry about right now, but they consider that there are some quantum operations which do some phase shift and some sort of changing in the phase in a plot sphere or whatever. You don't need to worry about. Right now just think that there are two quantum systems and there are two quantum operations and there is a quantum system which will feed the system with some sort of state, maybe ground or excited state, whatever. So basically, and when we do our operation from these two operations, we get a new operation and a new system which is called U, unitary operation, and we will get a conclusion as U is equal to P and A. It's not A and B, it's B and A, because there are some laws in linear algebra when we work with quantum systems and quantum computing. That's why we will use this law and give the multiplication as B and A. When we represent them in diagrams, we represent them as A and B, but when we put them inside equation, we put them like B and A. I know it's confusing and it's a valid reason to get confused, but there is no solid valid reason to worry about and discuss that why it is this way. Because when you multiply matrices, you have to consider about the initial and end of the product, because multiplication is not commutative. When you multiply B and A, when you multiply A and B, there are different results. That's why we will follow this rule, and it will be U is equal to B and A. And this is the multiplication loop, and this is summation of B for every value of I and AI and every value of A j. For every value V I j, we have every value of B and I with respect to K, and we will continue this loop again and again and again. And now I will try to help you visualize this in terms of interference vector. Like if you have a 1 point, you open it for different possibilities, like many possibilities. How many you can many you can draw, and then you put them in one possibility as the closing part. Like we talked about interference in the previous videos with probability amplitudes. So consider that we have 4, 5. I've drawn 5 dots. So consider this is a quantum system with value. What do I name it with? J. Okay. So this is a quantum system with J values, and then we continue it with quantum system with K values, and then with a quantum system with I values. And when we start from this position, like at any state, we open possibilities for many states. Like we open possibilities for 5 different states. And this is what we got in the term. When we multiply every I with every j with every k, like for every j, we get it summation by every k. Like this is summation k with every k and every k for every I and every j. And right now we will talk about j, and then we get from j and we open possibilities for every k, and then we close it for any single I. Like from 1 to many, and then from many to 1. Okay, so this is very beautiful if you consider this from a different perspective, but this actually shows you the interference vector. It actually starts from 1 point, open possibilities for many, and then closes at 1 point. Like I have shown in the previous video, quantum system starts from this Ramsey interferometry diagram, in which we have two systems here, and we have a phase shift here and a phase shift here. We start from this position, we go there, and we go there, and then again we start from this position, we go there and we go there, and we are ended in our result section of the event. We have a starting point here, and then we have two phase shifts here. 5. So this is actually showing the same thing, but for many possibilities, like for matrix multiplication, we have different values for different kind of matrices, and this is actually showing the beautiful result in matrix representation. You go there, you choose this path, and you go there, have a phase shift, and you go there and end your result with the event. And then again, you start from there, and you go this path. You did the second phase shift, and you go there and end this part. Like you have followed every different possibilities in this way. Right now we have two here, but this actually shows you a bigger picture that you can have many possibilities going through it, but it actually gives you a one result, one v I and j value based on the loop which it is following from every k and every j, every k for every I and j. Okay, I think it will be a bit confusing, but when you stop worrying about everything else here and you just focus on this part and get the intuition that for every j you go for every k, and then for every k you sum up every k and you get for every I. This is totally the easiest part. And then for every this part you have another loop, and then for every j you have another loop, and this continues until you are short with the parameters. And this is the Ramsey interferometry diagram, which actually shows another way, which I have shown previously, but I want to simulate and relate both of them, so you can actually see and realize that yes, they are important. So I think this lecture was really short and easy as well, because you don't need to get worried about depth or details or maths here. Just you get to know about the matrix multiplication for every value and for every point. That's it. Thank you.